Hi, in this video we are going to have a look at quite a complicated little equation that really takes our gas laws and kind of pulls them apart back to their kind of core concepts and then builds back up into a really nice little equation. So, as we've done quite a few times, let's start with our definitions because they're so important. Molecules are points, they don't attract each other, they move with a constant random motion. All of the collisions between the gas molecules and their container are elastic. And now we're going to add in a couple more now. The time taken for that collision must be very small by comparison to the time between all of the collisions. We're going to add a next one which pulls on our ideal gas laws that says any sample of an ideal gas contains a very large number of molecules. So we're going to be using the fact that we need a statistically significant sample. Okay, so if you take a sample of gas, we need this statistical significance because you will have a range of speeds. A very few molecules are going to be moving with extremely high speeds, and a few of them are going to be moving with low speeds, and there'll be a very nearly normal distribution. It's not quite normal distribution, it's actually a Boltzmann distribution. So the idea here is that the speed of an individual molecule is going to change when it collides with another molecule, but the distribution of them all remains about the same. And it's this distribution which changes with temperature. So the peak here to the left in blue, that's for a colder gas. And as your gas gets hotter and hotter, as your individual molecules increase the energy, you have a wider and wider spread of velocities. And so you can see the peak here moves towards the right. The probability of any one particle moving at a particular speed drops because actually with a higher range of speeds, you're still always going to have a few molecules that end up after their collisions not moving, and you're going to have some that are right up at the high end. So how do we take account of this spread? Well, we need to average it out in some way, but it's really useful to us to do that in a way that gives us a true indication of the kind of typical velocity or typical speed, and doing it this way removes all of the difficulties with the different directions and all of that kind of issue when it comes to the velocity of one of these little molecules. Now, at the moment, we're just talking about one direction. So in any one direction, the RMS value is going to be calculated like this. To give you a typical value, if you take the RMS speed air, and you step that through, so that is 3 times the pressure over the density. It's a little unfortunate that the font is a little bit is quite similar here. If you crank that through, you get about 2.33 times 10 to the 5 meters squared seconds to the -2, which seems a bit bonkers, but when you work that down through, you get 483 meters per second, which is about what you'd expect. It's a little bit quicker than the speed of sound. You need those molecules to be moving quicker than the speed of sound in order for them to propagate the wave at that rate. Think about it, they've got to oscillate a little bit in order to transfer the information. They must be, in those oscillations, moving more rapidly than sound. Okay, so let's take one of those little molecules and let's stick it in a box and let it bounce around for a little while and see what happens. So I'm going to take some molecules. I'm going to use the letter n because I'm going to be building up an algebraic expression. I'm going to say that each of those molecules has a mass of m, and I'm going to put them in a volume, v, and that volume has some dimensions. I've chosen here Lx, Ly, and Lz for my x, y, and z direction, respectively. So my little molecule can be moving in the x, the y, or the z direction. And so by convention, I'm going to use u, v, and w for the velocities. This is a fairly typical way of dealing with velocities in x, y. So the speed of this molecule is going to be given by the speed in u and v and w squared and the square root of all of that. I'm just using some simple Pythagorean mathematics. So let's think about what happens when this molecule comes stomping across this little box and it strikes the face. Because of our assumption that the collisions are entirely elastic and therefore we don't lose any energy, we are not going to be changing the energy of the particle. And so its velocity will go from plus u in one direction to minus u in the other. Notice that we're ignoring the other components. It may be moving in all 3 dimensions. It doesn't matter. If we just look at the x component, that u value, it will go from plus u to minus u. So the momentum then must change from mu to minus mu. The total change is 2mu. And so if there is a time between successive impacts, then we've got a change in momentum and a time. And so we can say, actually, we can start pulling this time in to Newton's second law. So let's do that. Let's take Newton's second law of motion. Force exerted on the molecule during the collision with the box, and therefore the force exerted on the wall, is just that momentum change, 2mu, over the time taken. So 2mu over t, we're assuming that because the box has dimension x and we're moving with time t, then don't forget that we're able to talk about how the collisions are spaced out in time by how long it takes that molecule to travel across the box. So that's why I've changed my expression here to 2lx over u. So the distance from one side across to the other wall and back again, divided by the velocity, that's going to give me the time between the collisions of this molecule and that right-hand wall. It'll collide, travel all the way across the box, bounce off the other wall, which we don't care about at the moment, we're not looking at that, and then travel all the way back again and strike the. So that's the time I'm interested in, and that's why I'm using this. Now, 2mu over 2lx over u is going to give me this. And so I end up with a fairly useful expression here of some kind of an mu squared over lx. I know that if the force on the particle is in one direction, then the force on the wall of the box must be in the other direction. And I also know that pressure is force over area. So the pressure exerted by each individual molecule is going to be the force over the area of the face. So for our x face here, that's going to be Lz multiplied by Ly to give me the area over which that force acts. So substituting this in and working it through, I end up with an expression for the total pressure exerted by a number of n molecules, given like this. So for the first molecule, I've got the change in momentum over the volume. For the second, I've got the same thing, and for the third and for the fourth, all the way up to n. I'm going to rewrite this. I'm going to rewrite this. And then I'm going to call back to that mean value of u squared. I'm going to call back to it, and I'm going to say that that is given by the square of the addition of all of these things over the number of particles. And so therefore I can write that top expression much more simply. I can say that it's simply going to be the mass times the number of molecules times that mean value. All of that lot over the volume. Now, because they're moving randomly in all directions, I can also say that the same expression would be true for V, so the direction in the y-axis, and W, the movement in the z-axis. And so I've got the x, the y, and the z axes all together in 3 expressions. So let's combine those 3 expressions. So 3p is going to give me an m plus the mean of all of those things over v. Calling back to earlier, I know that the RMS value is u squared plus v squared w squared, and so I can say that the mean RMS value, if you like, the CRMS squared value, is what I want in here. Okay, so I end up with this expression: 3 times the pressure times the volume must be the number of molecules times the mass multiplied by the RMS speed squared. If you like, PV is 1/3 nm CRMS. This is the equation which you will see in your formula booklet, and your students will have to use, relating the speed of the molecules to the pressure and the volume. I really like this because it takes our gas laws and it really kind of connects our gas laws to the physical model that we're talking about. This idea of little particles zipping around and colliding with the walls of our container. So if these things are moving, then they must have energy, so we can start to talk about how much energy is contained within the gas because of these things zipping around. So let's do that. Let's take that expression and our ideal gas equation, and let's put them together. If I keep doing that, or if I do that and I look at one average molecule as we're talking about, so that CRMS value, I have got 1/3 of m CRMS squared is k, multiply both sides by 2, just to make it look a little bit neater, and you see that what falls out is a 1/2 mv squared, or more properly, a 1/2 m CRMS squared must be equal to 3/2 kT. So temperature times a constant is the energy of the gas. We are showing that the average energy is proportional to the absolute temperature.